work is done upon an object whenever a force acts upon it and it leads to a displacement of the object. In all instances in which work is done, there is an object that supplies the force in order to do the work. For example, when a book is lifted to the top shelf, we supply the force to do the work on the book. When a plow is displaced across a field, usually a tractor supplies the force to do the work on the plow. Similarly, when a weightlifter lifts a barbell, he supplies a force to do work on the barbell. In all the cases, the objects doing the work, such as a student, a tractor, or a weightlifter, uses their stored chemical potential energy to transform it into work. In general, energy is the ability to do work. In other words, the capacity of an object to do work is called the energy of the object. We can say that the energy is stored work. In the process of doing work, the object which is doing the work exchanges energy with the object upon which the work is done. When the work is done upon the object, that object gains energy, whereas the other object loses the energy. This gain or loss in energy by the objects is known as mechanical energy. An object which possesses mechanical energy is able to do work. Similar to work, energy is a scalar quantity and it has the same unit as that of work. SI unit of energy is joule. In general, mechanical energy is the energy that is possessed by an object due to its motion or due to its position or due to its shape, such as when a fast-moving ball hits a stationary wicket, the stumps are thrown away. Here, stumps get the energy by virtue of motion of the ball. When a hammer raised to a height is allowed to fall on a nail placed on a wooden piece, it drives the nail into the wood. Here, the hammer gets the energy by virtue of position, which is further transferred to the nail. When rubber band of a catapult is pulled while holding a small object in its fold, on releasing the rubber band, it accelerates the object with a large speed. Here, the object gets the energy by virtue of change in the shape of the rubber band. Mechanical energy can be described as the kinetic energy and potential energy present in the components of a mechanical system. The word kinetic is derived from the Greek word kinesis, which means motion. Any object in motion has a capacity to do work. Everyone is well aware of a cyclone. It can destroy houses and roads. This shows that air in motion has a great capacity to do work. Moving air, that is, the wind, is used to turn the wheels of the windmills, which in turn is used to generate the electricity. Wind is also used to move sailboats. Similar to air, water in motion also has a great capacity to do work, such as running water is used to turn the wheels in hydroelectric power stations. When the wrecking ball of a demolishing machine is in motion, upon hitting a building, it demolishes the building. Similarly, when a hammer is allowed to fall on a nail placed on a wooden piece, it drives the nail into the wood. These examples show that a moving object is capable of doing work because of its motion and energy possessed by the object by virtue of its motion is called kinetic energy. Some examples of kinetic energy are a swinging pendulum, a heartbeat, running water, moving air, a moving fan, and a running boy. In terms of physics, a goods train coasting along a level track does not perform any work because force and displacement are perpendicular to each other. But it has energy and has the ability to do work. An object which has motion has kinetic energy, whether it is vertical or a horizontal motion. There are many forms of kinetic energy. For example, vibrational kinetic energy, that is the energy due to vibrational motion. Rotational kinetic energy, that is the energy due to rotational motion. And translational kinetic energy, that is the energy due to linear motion. In general, kinetic energy is commonly referred to translational kinetic energy. It has been observed that a massive fast-moving body has more kinetic energy than a light and slow-moving body. That is, the kinetic energy is related to mass as well as velocity of the body. Kinetic energy of a moving body can be measured by the amount of work that the moving body can perform before coming to rest. Let us consider a body of mass m and moving with the velocity v, and its motion is opposed by a constant force F. As a result of the opposing force, the body gets uniform retardation and comes to rest after covering a displacement S. Therefore, work done by the body against the opposing force can be measured as the product of the force and the displacement. Since at the end of the motion, body comes to rest and it has no motion, thereby it has no kinetic energy. So, we can say that all the kinetic energy has been used up in doing work. In other words, the work done against the opposing force F is also equal to the kinetic energy of the body. According to the Newton's second law of motion, force F is equal to the product of mass m and acceleration a. Therefore, the work done against the opposing force F becomes equal to the product of the mass, acceleration, and the displacement of the body. Here, negative sign shows that the force and the displacement are in the opposite direction. Since the initial velocity of the body is v, and after a displacement s, it comes to rest. Therefore, by using the third equation of motion, we can obtain v square equal to twice of as. Here again, negative sign shows that the motion is a retarding motion. On substituting the values of minus as, we get the work done against the opposing force F, or the kinetic energy of the body, which comes out to be half of mv square. This equation reveals that the kinetic energy of a body is directly proportional to its mass as well as to the square of its velocity. That means, for a twofold increase in speed, the kinetic energy will increase by a factor of 4. And if the speed becomes half, the kinetic energy will become 1/4. Similarly, if the mass of the body is doubled, then its kinetic energy also gets doubled. And if the mass of the body becomes halved, then its kinetic energy also gets halved. Let us measure the kinetic energy of a ball of mass 250 gram moving at a speed of 20 centimeter per second. And it comes out to be 0.005 joules. Similarly, if a hammer of mass 1 kg falls on a nail placed on a wooden piece from a height of 1 meter, then measure how much kinetic energy will the hammer have just before hitting the nail. By using the second equation of motion, kinetic energy of the hammer comes out to be 10 joule as shown. A brick lying on the ground has no energy and it cannot do any work. But when we lift the brick to a vertical position above the ground, it possesses some mechanical energy. If the brick falls down, then the stored mechanical energy has the ability to do some work. A dart gun is still another example of how mechanical energy of an object can do work on another object. When a dart gun is loaded, the spring of the gun is compressed and it also possesses some mechanical energy. The mechanical energy of the compressed spring gives the springs the ability to do work on the dart. While stretching the rubber band of a catapult, climbing the stairs of a diving board, or lifting a weight, we spend our energy in doing each of these works. And the loss of energy from our body is stored in the catapult's rubber band, raised body weight, or the raised weight. In these examples, energy is inactive at the moment, but has the potential to do work. Example, when the rubber band of the catapult is released, the stone flies away. The diver falls into the swimming pool and the weight falls to the ground and the stored energy changes to kinetic energy. Thereby, we can say that a positional object has capacity of doing work because of its position. The energy stored due to the position of the object or due to change in its shape is referred to as potential energy. Potential energy of a body is the stored energy by virtue of its position or by virtue of change in its shape. The energy stored due to the vertical position of a body is referred to as gravitational potential energy. This energy is stored as the result of gravity, whereas the energy stored in elastic materials as a result of change in their shapes is referred to as elastic potential energy. In general, potential energy is commonly referred to as gravitational potential energy. A heavy wrecking ball of a demolition machine is storing energy when it is held at an elevated position. This stored energy is an example of gravitational potential energy. Similarly, a drawn bow is able to store energy as a result of its position. This stored energy in the bow is an example of elastic potential energy. The gravitational potential energy of a body depends on two variables: the mass of the body and the height to which it is raised. It has been observed that more massive is the body, greater gravitational potential energy it has. Similarly, higher the height of the body, the greater will be the gravitational potential energy. This shows that there is a direct relation between gravitational potential energy and the mass of the body as well as the height of the body. Potential energy of a body is due to its height above the earth, and it is equal to the work done on the body in lifting the body against gravity to that position. If a body of mass m is to be raised to a height h above the ground, the force acting on the body is same as the weight of the body, and this force acts in the downward direction. To lift the body against gravity to the height h from its original position, we have to do work on the body that can be measured as the product of the weight and the increase in the height of the body. This work done is the increase in gravitational potential energy of the body with respect to its original position. If the gravitational potential energy of the body at the ground is 0, then this increase in potential energy is stored in the body as gravitational potential energy. Therefore, potential energy is equal to mgh. That means, for a twofold increase in height, the potential energy also increases by a factor of 2. If the mass of the body is doubled, then its potential energy also gets doubled. If an object of mass 2 kg is raised through a height h and its potential energy is increased by 1 joule, then calculate the height h. It can be seen that the height h comes out to be 0.05 meter.